Okay. Hello everyone. I am Prathmesh. In this video, you will get to learn about linear regression and gradient descent, beginner's approach. We will be explaining a very simple approach to linear regression and gradient descent. Um, we will not go into extreme fundamental and technical details. I am Prathmesh Patil, and I will personally explain you the theory behind linear regression and gradient descent, and then Subham will explain you how to implement these algorithms in practice. So linear regression and gradient descent are one of the most famous algorithms that we see in machine learning, which help you develop a relationship between your input variable and your output variable. So let's begin. So before getting into or before trying to understand what is linear regression and gradient descent, let us first take a very simple example. So let's say we have the height and weight data for 7 students, as can be seen on the screen. And now we want to find the weight of the 8th student based on his or her height. So how will we do this? That is the question. So one natural way to do it would be that, let's say, if I can somehow find a relationship between the height and weight parameter, well, then whatever the relationship will be, using that relationship, I can predict or at least make an attempt to make a guess at the weight of the student based on his or her height. So to find out such kind of what kind of relationship might exist, we will plot this data. And once you plot this data, as you can see on the screen, I have added some extra points just to make it more visible. So you will see that immediately that there's a very linear kind of relationship between the height and weight of the students. And let's say somehow if I can find this line or this linear equation which will describe the relationship between the height and weight, well, then I am done. Then all I will need is that just take the height of the student and input in that linear equation, and then I will get my weight, or at least the predicted weight. And this is the idea. So this is what linear regression does. This is the central theme of linear regression, that it will help you find out a linear relationship between your input variable and output variable. Okay, so speaking a bit more formally, linear regression is a statistical method to determine the strength and relationship between two variables. So, for example, generally taller people tend to be tend to have more weight. And well, how will you model this relationship? So to model such relationships, we in general use something called as regression analysis. Now there could be multiple ways of regression analysis when there is a single input variable involved. For example, in our case, we were just trying to find the relationship of weight with height. So this is known as simple linear regression. And most of our discussion would be focused on simple linear regression. But let's say in case you want to model weight of a student, not just as a function of height, but other parameters as well, as, for example, what is their daily calorific intake or something else. Then in that case, what we will have is something known as multiple linear regression. Okay, moving forward, so linear regression is a supervised learning model. If you don't know what a supervised learning model is, well, basically in machine learning, supervised learning model is where you have an input variable x and an output variable y, and you're trying to find a function f such that y can be modeled as a function of x. Okay, so now you have your data set x1, y1 up to x and yn. I'm sorry for the error. This should be y1. Then your goal is to find a function which will model your relationship. We call that function as f of w and b, where w and b are unknown. So, and let's say somehow we can find this function for the moment. So once you have this function, then the question is how will you use for prediction? So how to use this function for prediction? So let's say you are given new input value x star, then we will just predict the output or y by simply calculating FWB of x star. So now to find this target function, our biggest challenge is how will you find out w and b. So for that, now I will get into mathematical details of this calculation. So kindly bear with me. Okay, so mathematically speaking, relationships of the form y is equal to wx plus b plus epsilon is called a simple linear regression model, as I said earlier, where b is the intercept and w is the slope of the line, and the epsilon term that we have here is what we call as the error component. And generally the assumption is that the expectation or the mean of the error is 0. So if you take the expectation on both the sides, you'll get expectation of y is equal to wx plus b. Now the estimator of e of y is generally known as expectation. The estimator of expectation of y, namely y hat, can be obtained by the estimators of w hat plus b hat of w and b. Then the fitted regression line we are looking for is given by y hat is equal to w hat x plus b hat. Okay, so if in case you did not understand what I just said, basically what I'm trying to say is that the function which will estimate your output, or for in our case it would be f of wb, the function fwb. That function can be found if you have the optimal values for w and b, and optimal values of w and b are w hat and b hat namely. So this is again, I'm repeating what I said earlier in a bit of more formal and statistical knowledge. And well, once you have w hat and b hat, well then you're done, and then your function is ready to use. So now the question is, how does linear regression find these functions? So let's go back to the graph that we had, and from there I'll explain how to do this. So how the main idea behind this is that in linear regression we try to minimize the actual predicted value, and so we try to minimize the difference between the actual outcome and the predicted value. So you see that these points that you have, they are not exactly on the line, they are slightly away from this line. But the line that we have chosen is such that the difference between the predicted value, the difference between the actual value and the predicted value, the sum of these error terms, as say, which we'll see what is it in the future, is minimum. That is the main idea. So let's go ahead. So the deviation of observed values yi from its predicted value yi hat is called the ith residual. So on your training data set, what you will have is that you will come up with a equation and for FWB, and on your training data set you already know your output, and using your prediction model FWB you can predict the value, and so you will find out the difference between your predicted value and your actual observed value, and this is called as the residual. Now what you do is that you take the square of these residual terms. Why are we taking the square in particular? Well, you see, in general, this error could be either positive or negative. So if you just take the sum of these terms, well, then, you know, these errors might cancel out each other, and the model that you get or the equation that you get might not be the optimal solution. So, but when you square these terms, well, then each term is positive. And now if you try to minimize this error, as I said earlier, then, well, then the model you will end up with will truly be an optimal model. So again, as I said, the goal is that you want to minimize the error terms. You want to find W hat and beta hat such that your EI terms for each I is as minimum as possible. So now once you have the optimal W hat and B hat, then you will get the least square fit line. So the least square fit line is the one, as I said, for which the sum of square error value is minimum. And now, since immediately as a mathematical fact, it follows that if SSC is minimum, then its partial derivative with respect to W and B must be 0. So this is just the same line written in mathematical format. And then just substitute the equation of SSC in this equation and calculate the derivatives. And once you calculate this derivative, you will get this nice linear equation that we have. And similarly, if you take the derivative of the sum of square of errors with respect to W, then you'll again get an equation. And now we have two equations in two unknown variables, W hat and B hat. And so you can solve these equations. And once you solve this equation, then you will get this very scary looking two representations of W and B. But you need not be scared of these equations because, well, it will be your computer which will be doing most of these calculations. Now moving forward, so now we have something about loss function. So see, our entire calculation now depends on this sum of square of errors, right? So here what we did was, since adding simply error terms directly, we may or may not get you the best solution. So we squared these terms and then added them. So instead of just squaring them, you can do something else. Like, for example, take the mod of each error and then add them, or some other equation. So this is known as the loss function. So in general, the equation that we have here, summation of EI square can be replaced by this equation, summation of L of EI, where L is the loss function. And as I said, your loss function could be your square or absolute function, or you can have in general any even power of X, even power of E, and all of these are valid functions. And just a small caution that I will like to place at this point, that our entire calculation here that we did was for the square error. So these equations that you have will only work if you are using the square error. If you are using some other function, for example, well then in that case, then you will need to again compute the solution by using these two equations. And the equation that you will get for W hat and B hat will be different in different cases. Moving forward, so there were some implicit assumptions that we made. First of all, we assume that Y and X have a linear relationships. So in general, this may not be true. So what will you do in this case? So let's say Y has a polynomial relationship with X. Well, in that case, you will need to do something called as a polynomial regression. But we are not discussing that here. Second is that we assume that the expectation of the error component is 0. So if your expectation or the mean of your error is not 0, well then first you will need to adjust your data for these fact. And lastly, we assume that all our observations are independent. So x1, y1, the first observation that you make does not have any effect on the upcoming observations, and so on and so forth. This is an implicit assumption that we made. And then, well, there are some shortcomings of simple linear regression as well. Well, so you see, for the square error loss function, we had a very nice equation of w hat and b hat. Such a nice solution might not always exist. And well, as you go in higher dimensions, well, even if the solution exists or there is a very nice equation, it might be computationally a bit more expensive. So the next thing that we will see, we'll try to find a solution or try to overcome these equations. Okay, so this is where we left, and I said that just before that, simple linear regression has some issues, and those issues are that, well, the nice equation that we develop for W and B might not exist all the time, and well, in higher dimensions, it could be computationally expensive. So to tackle these issues, we have a new algorithm, a different kind of algorithm, which also tries to do linear regression, but the approach is slightly different, and that algorithm is known as the gradient descent algorithm. So how does gradient descent algorithm work? So let's say you have a bunch of data points, as you can see on the screen. So what the gradient descent algorithm, or the basic idea of gradient descent algorithm, is that it will pick up a random point from this data set. Let's say it picks this one. Sorry. And then it will try to fit the line such that the error or the loss, which is the difference between the actual value and the predicted value. So y hat minus yi. This difference is minimized. Then it will take another point, repeat the same process, and this recursion will go on over the whole data set. And finally, you will end up with a line which is an optimal solution. That's the idea. In case it is not clear, so as you can see, you will get such multiple lines. So let's say you started with the point. Let's say you started with this point, and the initial line that you had was the green line, and then you add another point, and you will get this red line maybe after to accommodate both the points. Then later on you add another point, and you will end up with the third line, which is the blue line. So in this way, this sequential update of linear fit goes on. Although this diagram in particular is for just understanding purpose only. So this is just, I'm trying to explain that, okay, this is how gradually the line shifts and finally reaches its optimum value. In practice, when you'll apply gradient descent, you might not see this. You will not see this. Anyways, moving forward. So what is the general procedure of gradient descent? So the idea is you start with a random point, calculate the gradient at that point, then make a scale step in the direction of the negative gradient. So why are we moving in the direction of the negative gradient? So your f function here is the loss function, and we want to minimize the loss. So if you move in the negative direction of the gradient, that will be the direction in which the loss function is decreasing. And so that's why we always move in the direction of the negative gradient. If you want, if in some case, when let's say your goal is to maximize the gradient, the whatever function you have, well, then you will move in the positive direction, and this will become plus. Okay, and then we keep on repeating these two steps till either we exhaust the number of iterations that we are allowed to, or in case, let's say, you end up in a situation, let's say, for example, where this line, even after addition of point, is not changing very much. It's more or less the same. Well, in that case, you have already reached the optimal solution, and such slight changes will not affect your solution in any way. So you're just wasting your time. So we put this condition that once your change in the gradient drops below a certain threshold, we terminate the procedure. So that's the general idea of gradient descent. But here you see there's one important factor, which is this eta. I did not explain what this eta is. So this eta is actually called the learning rate. And well, how is it important? So you see, just give me a moment. Yeah. So this eta is the factor which appears before the gradient. So what it will do is it will essentially control the effect of your error term that you have. So if your eta is small, then well, the corresponding effect of loss function or the error term will be minimized. Whereas if your eta is large, well, then your error term will have much higher effect. Yeah, so just as I said, the eta appearing in the above equation is called the learning rate. It is also the hyperparameter. Well, hyperparameter, if you don't know, is it's the parameter which controls the inductive bias. So the smaller learning rate or the small value of eta generally implies that the gradient descent algorithm will take longer to converge, because you see, when you have a small eta, what will happen is that the effect of the loss function will be not very much. So the gradient descent algorithm will need longer and longer, much longer iterations to finally arrive at a optimal value. And in some cases, if your eta is too small, well, then it may happen that you might reach your maximum iteration before reaching the optimum point. If your learning rate is too big, well, then the algorithm will converge faster, but if it's too large, well, then it will jump around and you might not might not converge to an optimal solution or even diverge completely. So you have to be careful while choosing your learning rate. Generally, a smaller learning rate is preferred, something like 0.1 or 0.2. Yeah. Now coming to the different types of gradient descent algorithms that we have. So as we were discussing in the great idea that I discussed, in that idea, we were adding each point. In every iteration, I added a point, and then I adjusted my line according to minimize the error function. But instead of so this is generally known as the stochastic gradient descent. So in stochastic gradient descent, you will start with a random point, then you will fit the line, then you will add another point, then you will fit the line as such to minimize the loss for both of them, and so on and so forth. The process continues. In batch gradient descent, what happens is that you will take the entire data set in the very beginning, and you will calculate the total loss function. Then you will find a line to minimize this loss function, and then each iteration will be over the entire data set. So you take the entire data set, find a line, fit it, then you again try it, and then again your line improves a bit, and then again these iterations go on and so on and so forth. But this could be a little bit computationally expensive. So what we do is instead that sometimes we can divide our whole data set into small groups, each of which is called the mini batch. And then you calculate the total error of the mini batch, try to find a line which will minimize the loss for that batch. Then you move on to the next batch, and so on and so on. And that's how you finally arrive at the optimal solution. This is known as mini batch gradient descent. Just a comparison now between both the factors, stochastic gradient descent and batch gradient descent. So as I said, batch gradient descent is iterating over, in each iteration you are computing over the entire data set. So batch gradient descent, or BGD, as expected, is very expensive. So for large data sets, generally stochastic gradient descent is preferred. But stochastic gradient descent, you see, since you are iterating over each point, it may happen in a situation where you are minimizing the error for individual points, but the total error is not getting minimized. Such kind of situations might happen because of outliers maybe or something like that. So the solution that the stochastic gradient descent gives is a good solution, but it is not necessarily optimal. Whereas batch gradient descent, although it is computationally expensive and it takes long time, but the solution it will give will be such that the total loss is minimized, so it's an optimal solution. And lastly, stochastic gradient descent achieves convergence much faster, well, because it is computationally easy, so it will converge much faster. Now moving forward. So next, before understanding the limitations, let's first understand what is a convex function. So a convex function, this is a mathematical definition. A function is called convex if for parameter lambda in 0 to 1, any 2 points a, b in the domain, f of lambda a plus 1 minus lambda b is less than equal to lambda fa plus 1 minus lambda fb. And so the limitations are that the gradient descent algorithm can only be, applied to functions which are differentiable and convex. So what happens when the function is not differentiable or it is not convex? Well, first of all, if it is not differentiable, then well, how will you calculate the gradient at that point, and the function and the entire procedure fails. But if your function is not convex, then actually what happens is that you might have some kind of a saddle point or a local maxima where the function where the gradient descent algorithm will get stuck, and from there actually reaching a point which is actually the global minimum, or the point where the loss function is minimum, it becomes very difficult to approach. So this is one of the limitations of gradient descent algorithms. And well, the references that we have used is so the mathematical calculations about simple linear regression that we were using is based on the book Sokos and Ramchandran, Mathematical Statistics with Applications. And we have also taken help from this particular website, Towards Data Science. If you want to read further about these things, you can refer to these books and this website. And thank you. Now.
Hello everyone. Today we are going to implement linear regression using the linear regression package from sklearn and by using the batch gradient descent. So first we will see the linear regression implementation using sklearn. The code is divided into 3 parts. First is the dataset generation. We will be generating our own dataset for this purpose. Second is the fitting of our dataset into the linear regression model. And third is plotting the results. So now the first part, which is the dataset generation. So in the code, it starts from line 7 and goes up to line 35. Here we will be generating a 2D dataset which has some linear correlation among itself. So you can see that in line 13 and 14, we have declared two lists, x underscore a and y underscore a, which will be storing the x and the y coordinates for our datasets. In line 16 to 18, we have generated our x coordinates using a randin function, which generates the random integers within the specified range. Here we have used the range 1 to 100. You can choose a range of your own, and we have stored the respective x coordinates into the list x underscore a. Now for generating the y coordinates, we actually need a value of slope and the value of intercept. So in line 20, in variable m, which is the slope, we are storing the slope of 1 by root 3. You can obviously take a slope of your own. After that, in the for loop from lines 20 to 26, we use the value of m and we randomly generate a c using the uniform function. And for each value of x or the x coordinates, we generate the corresponding y coordinate using the equation of the straight line. And after this, we store all these y coordinates into the list y underscore a. Now, one thing is to be pointed out is that linear regression package of the sklearn requires its input in the form of a 2D array. So in lines 28 and 31, we convert the x and the y coordinates from the list to array using an array function. And then in lines 29 to 32, we convert them to a 2D array of dimension 100 cross 1 using the reshape function. So after this, we are done with our first part and we are moving to the second part, which is our fitting of the datasets into the model. It is in lines 37 to 42. So as you can see in line 38, we imported our required package, which is the linear regression package of from sklearn.linear model. In line 40, we have declared a model variable, which is the model. And then in line 42, sorry, in line 41, we use the fit method of linear regression to learn from the dataset or the given dataset. And in line 42, we predicted the y coordinates of the x values of our dataset using the predicted model, and we stored the respective y coordinates of the x in the variable y prddlr. Now, after this prediction has been done, we are only left with the plotting of the results. So the third part goes from lines 47 to 61. In line 47, we imported the pyplot package for plotting. Lines 49 to 53 actually plots the data sets, the corresponding original data sets which we created using the blue color. You can see the data set in the upper right corner of, you can see the data. So here is the data set, which you can see having some linear correlation with it. And you can see the data set in the upper right corner. And in line 56 to 61, we plot the linear regression or the fitted model which we learned by linear regression method using a red color. So after plotting the linear regression model, it looks like this. So this is what we plotted using linear regression. So once we are done with the linear regression model. So in this way we implemented linear regression using the sklearn package. The next thing we will be going to do is that we will implement linear regression using batch gradient descent method. So now we are going to implement or going to learn to implement linear regression using gradient descent method. So you will be looking at this piece of code on the left side of the screen, and we will also be referring to some of the to these three equations which you can see on the right hand side of the screen. So let's start. So initially in line 46, we have declared a variable cost, and we have initialized to a very large number. The reason there is a reason behind it. I will get to that in a minute. After that, TA, we have declared a variable TA, which is nothing but an intermediate variable, which we are going to use. M is the slope of the line, which we are going to learn from by the gradient descent method. C is the intercept. Alpha is the learning rate. And Y pred GD is actually a value which actually a list which contains or stores the list of predicted Y values, which we predict using the gradient descent method. So initially we initialize all the values of Y predicted with 0 in the for loops of line 52 to 53. After that, in for loop in the lines 55 to 56, we calculate the cost using those Y predicted values. So here we use TA. TA, as you can see in the right hand side, in the first equation in the right hand side, TA actually stores the values up to the summation part, up to the yi minus y predicted square, and the sum of all those yi's from 0 to n. TA actually stores this value. Now now when TA is divided by n, which is the number of data points, we actually get the cost function. So TA when divided, we have done the same thing in line 58. We have divided TA with the number of data points, and we have stored it in a variable called previous cost. So now the question comes is that why previous cost? So the logic behind gradient descent is that we update the values of M and C until the cost function is reduced to as much as we want. So the logic behind the implementation of this coding is that we will have two cost functions, which is the normal cost variable, which is storing the cost, and the previous cost variable, which will store the cost in the previous iteration. And once the difference between these two, that is the current cost and the previous cost, becomes very minimal or becomes very less, we actually stop the gradient descent method. So as you can see in line 61 up to line 80, 90, the gradient descent method actually goes. So I'm going to explain each of the code line by line. So as you can see, in while loop, we check the absolute difference between previous cost and the cost. And this was actually the reason why we generated, why we initialized cost with a very high variable to create a very big difference between the previous cost and the current cost, which will get reduced in the subsequent iterations of the gradient descent loop. So here we have chosen that when the difference between the previous cost and the current cost is 0.00001, if it is greater than 0.00001, then the while loop runs, otherwise the while loop terminates. So once we enter into a while loop, so we are going to run a new iteration, right? So for that new iteration, we actually store the current cost function into the previous cost variable, and we will store the new cost which we are going to get in this iteration and in the cost variable. After that, there comes the variable TA, which we already know. Delta D cost actually stores the value, as you can see, D cost underscore M actually stores the value of the summation in the middle equation, xi into yi minus y bar, and the summation of all these xi's from 1 to n. This value is actually stored in the total cost underscore M. Similarly, in total cost, as you can see in line 67, total cost underscore C stores the summation part of the variable DC, D underscore C. And D cost M in line 64 and D cost M in line 65. These actually stores the entire value of DM, that is the derivative value which we get by the derivative which we get by derivative with respect to M. And D underscore C actually stores the total delta, total update value which we are going to get by derivative using C with respect to C. It is getting stored in DC. So first, in line 69 and 70 and 71, we actually calculate the total update we actually get while doing the while running the for loop for all the data points. We actually get the value of DM, which we will use to update the value of M. And in for loops at lines 74, 75 and 76, we actually get the value which we are going to use to update the value of C, that is DC. After that, in lines 79 and 81, you can see that we have updated the value of M and C using the specified alpha rate which we have declared in line 50. You can choose the alpha rate of your own. So actually the alpha rate and the this value of 0.0001, this value and the alpha rate actually determines for how much time the for loop is, or the while loop is going to run. Once we have updated the M and updated the C value, after that, with those updated values of M and C, we again calculate the Y predict in line 85. And using those Y predict, we again calculate the TA, that is the YI minus Y predicted square. And the TA when divided by the number of data points actually gives the cost. Now this new cost function is again gets compared with the previous cost function in the next iteration of the loop. And if the difference between two is still larger, the while loop runs. And if the difference between them is still smaller than 0.00001, then the while loop actually stops. So once the while loop stops, we come to the plotting function. So here we do nothing, but we on the very same data set, we can see this is actually the data set which we have generated during the linear regression plotting. And on this dataset, when we plot the line which we have learned using gradient descent, the line actually looks like this. So you can see we have executed the batch gradient descent and we get a line like this. So if you compare this line with the previous linear regression line, then you can see that there is a little small learning difference between those two lines. So it's actually the difference in the line actually depends on the number of iterations for which the while loop runs and also the learning rate. So that's all. This is how we implement the linear regression using batch gradient descent.
Once again, thank you from both of us for watching this video. Hope you have learned something, and thank you once again.